Hi class, and welcome to this next screencast, still talking about the chemistry of life and what life needs to survive. And one of the essential components to life is water. So let's take a closer look at water. And as we go through this, I kind of want you to think, how much water are you drinking? And as you learn about all of water's unique properties and what makes water so essential to life, maybe you'll think more about having a bottle of water instead of a can of Coke. So let's have some facts about water. 65% of the human body is water. 75% of the brain is water. 75% of a living tree is water. And you could survive about a month without food, but only 5 to 7 days without water, if that. So water is really, really important. So the question we're going to try to answer is, what's the deal with water? Well, water supports life. And in this video, we're going to talk about 4 main reasons or properties of water and how it supports life. But each one of those reasons is due to one thing. And it's because of a special type of bond. And it's a type of bond we didn't talk about in the first video. It's a hydrogen bond. So let's take a closer look at this really special bond of water. Now what we have here, this is one molecule of water. So this is your 2 hydrogens, and this is your oxygen. And so this is another molecule of water. So in total here, we're looking at 5 molecules of water. I just want you to get a picture of what you're looking at here. So now let's examine where the hydrogen bond is. It's right here. And a hydrogen bond is a bond between a hydrogen, so here's the hydrogen, and any other atom that likes electrons more than hydrogen does. And we call that being more electronegative. You don't necessarily have to know that, but that's just the name. And so oxygen actually likes electrons more. It draws electrons towards itself more so than hydrogen does. And so this is called a hydrogen bond. So oxygen, hydrogen, and that's a hydrogen bond. Another example would be between hydrogen and nitrogen. So let's take a closer look at all these properties of water and how they're all due to this essential bond called a hydrogen bond. Now, another thing about hydrogen bonds is that individually they're somewhat weak, but when you put a lot of water molecules together and there's a lot of hydrogen bonds, they're actually quite strong, and that's why water is so cool. So the first property is I want you to think about trees, right? Trees are in the ground and they've got these root systems that pick up all this water, but their leaves need water as well. And what if it's, not raining? Well, they need to get water from the roots up to the leaves. And how do they do that? Well, it's due to some special properties of water. The first is cohesion. Cohesion is simply when water bonds to itself. So this right here, water is bonding to itself. This is an example of cohesion. Another example of cohesion you see a lot probably, and it's surface tension. So a water strider can walk on top of the water because of these tight hydrogen bonds between the water molecules, creating a nice surface tension. The other force that's happening is adhesion. Adhesion is when water is bonding to something else. So for example, when water is bonding to the sides of the tree trunk. Okay, and that is moving the water up the tree. The combination of the cohesion sticking to one another and the adhesion sticking to the trees of the trunk. So together these forces are moving water up a tree. Now, I didn't give you the name of this process, but maybe as a little extra assignment, find out what the name of this process is, how trees get water up to the top of their leaves. So that's the first property, cohesion and adhesion. The second question I want to sort of introduce is, how does ocean life survive in the winter? Think about that. Okay, maybe you know the answer. But in the wintertime, we have ice, don't we? But ice floats, and that is really, really important to ocean life. Think about it. If the entire ocean froze and ice sunk to the bottom, it would kill all of the ocean life. But instead, that layer of ice on top creates this nice insulating cover to protect that ocean life. Now you might be wondering, well, why does ice float? I'm going to tell you. It's because when water freezes, we have these stable hydrogen bonds form between the water molecules. So here are these stable hydrogen bonds that are forming, and they sort of hold the water molecules at arm's length. So you can imagine just a whole bunch of water molecules, very stable, very rigid, holding each other at arm's length, and that's creating this crystal structure that is actually less dense than water, so that it does float on top of water. So that's the second really, really cool property of water. Cohesion, adhesion, and ice floats. Third, let's think about our oceans. Why do our oceans stay relatively the same temperature all year round? So whether it's wintertime and we've got freezing temperatures, or whether it's summertime and it's hot? Well, the answer is water moderates temperature. And the reason for this is that water has a high specific heat. This simply means it takes a ton of energy to even change water's temperature even just a few degrees. And again, you might be wondering, well, why? And the answer goes back to those hydrogen bonds. It is so hard to break that collection of hydrogen bonds in the ocean. So hard to break all those bonds. It takes a lot of energy to do that. So because of that, the temperature stays relatively the same temperature. So water moderates temperature. And the fourth and last unique property sort of explains why our body is made up of 65% of water. And the answer is the fourth property. Water is the universal solvent. A solvent is simply something that dissolves particles. And so this guy here is saying, my blood is mostly water, and I'm glad because it carries all of my nutrients throughout my body. It dissolves all of my nutrients and transports them. So why is water a universal solvent? Well, it's because it's polar. It has a negative end, that oxygen end, and it has a positive end. That's all that being polar means. It's got a positive end and a negative end. And so what happens is it can easily form hydrogen bonds surrounding charged solutes. So let's take a sodium positive ion, for example. All of the negative oxygens can surround that sodium, and as it does that, it's dissolving that sodium particle or whatever that sodium was a part of because of that negative interaction with that positive ion. So for example, salt water or sugar water. What we have there is the solute is the salt, and that's a charged particle. The solution is the salt water that's made, and the solvent is water. And so water is polar, and it's dissolving those charged particles just like you see in that figure here. So water is the universal solvent. Here's your checkpoint, and you can just click right on the answer. So let's go back to this idea of our blood and how much of our blood is actually water. This is a great thing, again, because water is neutral, right? It has a pH of 7, and blood pH is about 7.4. So it's a little on the basic side, but not much. It's pretty much neutral. So let's look at this pH scale. So bases are on this end of the pH scale, above 7 and up to 14 on the pH scale. Bleach, soap, ammonia, baking soda. Bases accept hydrogen ions from other atoms or molecules, or we can consider bases to donate hydroxide ions. So this is called a hydroxide ion. And on the other end of the pH scale, we have acids. So this is between 0 and up to 7 are acids. And acids donate hydrogen ions, and they're going to lower pH, lower towards the 1-2 end of the pH scale. Now, why are we talking about the pH scale? Well, life requires a very delicate balance of hydrogen ions and hydroxide ions. And our body has something really cool called buffers that are going to balance these ions out. And you're going to learn more about buffers with your homework assignment. So let's take a closer look at the pH scale. Each step, and this is something really interesting, each step on the pH scale is actually a factor of 10. Not a factor of 1 or 2, but a factor of 10. So again, from 7 to 8, it's going up 10. From 8 to 9, it's going up 10. Collectively, going from 7 to 9 is 100 because you're multiplying as you go up. It's a factor. So let's take a look at milk of magnesia. This is a pH of 10. It's actually 1,000 times as basic as distilled water, which has a pH of 7. So we go up 1, and that's 10. We go up 2, that's 100. We go up 3, and that's 1,000 times as basic. Here's just a real quick chart of some other pH levels in our body. Your human skin is slightly acidic, 5.5. So is your urine at 6.0. Blood, like I said, is a little bit basic. Your pancreas secretions are also a little bit basic. And here's your last checkpoint, so you can just click right on it. And your homework assignment. Your homework assignment is to take a picture, and you can honestly take it with your phone and bring it to class. I don't care. But take a picture, email it to yourself, email it to me, or you can draw one if you don't have a camera, of one of water's unique properties in action. So I want you to start be an observer and look around your world and observe water in action. Second piece of homework, research and be ready to explain one buffer in the human body and how it works.